And now we've got potentially one of the more interesting and challenging kind of structures. We're looking at kind of introducing nitrogen into this. And the previous lecture kind of touched on some of these points. So before we dig into it too much, what we should consider are differences between oxygen versus nitrogen. Because we're looking at an atom effect, we're really concerned about size and electronegativity. So to that end, size-wise, there's really no difference. Right? They're in the same row, so there isn't a significant difference as far as size. But where we are going to see a difference is electronegativity. Oxygen is more electronegative than nitrogen. And what is that going to do, or what does that mean for us? Okay, that means we should be putting more electrons, okay, on our oxygen in deference to our nitrogen. Okay, so if we look at now the reactivity of our carbonyls, a carbonyl has that electrophilic carbon. If I now want to react a nitrogen with it, one of those intermediate structures is going to have that carbon now sandwiched between an oxygen and a nitrogen. And let's not worry about charges per se. So now the question becomes, what happens? Okay. Should we stay in this state, or should there be some kind of imbalance that forces this out? We saw that when we had an oxygen come in as a new species, that a second oxygen could chase that first oxygen out, right? And that's how we got to our acetals. I know the geometry there is horrible. Since there really isn't a big difference between oxygen and nitrogen, if we now sub those out and say we have nitrogen come in, couldn't I theoretically have another nitrogen do that same system and chase out the oxygen to now take me to the structure of the acetal equivalent with two nitrogens? Okay, well, a lot of that is going to now depend on that difference in reactivity between our nitrogen and our oxygen. Oxygen wants more electrons. So if I'm looking at the initial state that I had here of new oxygens coming in, that same oxygen is going to be less willing to share. So I need a second oxygen to help kind of imbalance or balance out that carbon. In the case of nitrogen, however, because it is more willing to share, I actually don't need a second equivalent of the nitrogen. The very first nitrogen I add can be used to chase out the oxygen. Which means when I get to the product of this, I'm going to see a double bond to the nitrogen and our oxygen chilling out on its own. This is kind of a dilemma, and this really sets us up for actually the next unit, because in this process, I've done that nucleophilic addition. The nitrogen came in and attacked, but the end process is that I don't need a second nitrogen to come in. I'm using the first one. Okay? So now in that reaction, I'm now doing an elimination because I'm forming a pi bond, and I'm doing it by eliminating a nucleophile. So the nitrogen introduction in this chapter is really starting to introduce the concept of the nucleophilic addition and elimination. It doesn't quite fit the pattern perfectly, but it's starting to kind of direct us in that path. Okay, so to kind of help us think through this again, what I want you to do is we should attempt to run the reaction, okay, shown. Okay, and we want the second one. I want to see a mechanism for that. And by I want to see, I will draw one, but you should attempt a mechanism. Remember, we've done the acetal. Whoops, that was kind of weird. We've done the acetal mechanism. Okay, the nitrogen is pretty much the same thing. Oh, that's what happened. I did actually advance things. The nitrogen is effectively the same thing, except instead of it being oxygen as an alcohol, we're now throwing in the nitrogen. So run the mechanism for the reaction shown with the nitrogen, kind of like you would expect the acetal. If you need help, go back and look at the acetal and see what you can come up with, but draw out a mechanism for this. And that means you should pause so that you have time to draw that. Okay? But now I'm going to assume that you're back and you're with me and you have a mechanism that you can evaluate and look at. In this case, what I'm going to do is just say this nitrogen comes in, does the direct attack, my nucleophilic addition. The result, and I want to make sure I've got a lot of space here, so I'm going to go all the way over here. The result of this is that I have a new bond to my nitrogen, and I'm going to show all three hydrogens, and we'll see why in a second. Then I'll have my oxygen, I'll have my lone pair, extra lone pair on the oxygen, which would mean it's negative, and the nitrogen would be positive. Okay, so cool, that's a decent first step. We look at that, that's got lots of charge. That reaction does not seem likely, so this might be a good opportunity to say we should use a catalyst. Okay, and that we'll address in kind of detail after we've got this mechanism out. So if we continue this reaction, I don't like those charges. Okay, the first charge I'm going to address is the nitrogen one. Okay, and it actually makes sense to address the nitrogen one first because nitrogen's a half decent base. So a second equivalent of our nitrogen can come in and it can remove that hydrogen, and that would set me up. Still have the negative oxygen. Nitrogen, I'd have an NH2, and I now have this lone pair on that nitrogen. So all we're doing is running an acid-base step. So acid-base, the first one was a nucleophilic addition. We have that negative oxygen, right? So I would want to protonate it. Right? Oh, and of course I lose connectivity. Protonating it now is going to be kind of a challenge. What are we going to protonate it with? If we tried to use NH3, so NH3, we'd then be forming NH2 minus, which is a really strong base, a stronger base than O minus, which would suggest that reaction would reverse, and that doesn't work. Okay, so this ties back to this, we should be adding a catalyst issue. Okay, we could make the argument that the byproduct of that previous reaction was NH4 plus, and we could pick up the hydrogen that way. Okay, that is a decent argument, though the amount of NH4 floating around is now incredibly small because it's only being produced in that one step. Okay, so the likelihood that that would be a valid step is pretty slim. Okay, but there we go. Let's go ahead and say that we've got that. We have the NH2 still down below. We would now have our OH. This would be the approximate hemiacetal. Okay. In our mechanisms, if we were to continue on to form an acetal, we would need a second equivalent of the NH3. Okay, and we've got tons of it. It's a solvent. But if we ran under acidic conditions, we would have to protonate our oxygen first. Well, we didn't actually say if we were acidic or basic. Okay. Whoa, that seemed to undo a lot. Maybe it didn't. Okay, so what can we do here? And that does become a challenge. We would need to actually acknowledge what catalyst we should be using for this. If we go full-on strong acid catalyst, that becomes a problem because the nitrogen, as we said, was basic. And if we go full-on strong acid, we're going to neutralize that nucleophile. So we really need to run under kind of mildly acidic conditions. Those mild acidic conditions are not going to drive this step forward very well. Okay? But if we had a mild acid floating around, as a general, we could just say H+, we could protonate, kind of like we did with the acetal. The oxygen not wanting to be positive could then leave the structure. Okay? And you might say, well, but that wasn't a favorable reaction. You're right, but this is kind of what we're stuck. When I talked about equilibrium being problematic, this is one of those equilibrium being problematic things. If we continued this on, we would see the NH2 with our lone pair and positive, and we might go, well, dang, that looks really close to my product. What if I have these electrons swing in? Okay, really all I'd be showing is a resonance structure. Okay, and because that, let's just say I'd be showing a resonance structure, NH2, and I'm going to need that bond shown explicitly to my hydrogen here in a second, with that positive charge on my nitrogen. I could then have another equivalent of the NH3 floating around in solution, pull off that hydrogen, and I would now be at my product. So cool, that explains it, but why form that double bond? Remember, in the acetal, 2 oxygens came in. We see that up here. Okay, why is the nitrogen only having 1 nitrogen come in? Well, a lot of this has to do with that difference in chemistry between the nitrogen and the oxygen. That nitrogen is a much better electron donor, and so once it is attached to the structure, this step is easier for the nitrogen to do than it is for the oxygen. Right? Which means we can go through and do that full-on elimination, or in this case heterolysis, to form that pi bond with the nitrogen, and we would have ejected water. That's kind of neat. Okay, and that's one of the things that makes the nitrogen kind of cool, is it's really just an overactive oxygen, so you don't need to use quite as much, sort of, in massive air quotes that you can't see, but it allows us to do this kind of interesting chemistry where we end up kind of subbing oxygen for nitrogen, okay, which is cool. When we went through and did this, we actually stumbled across this issue of a catalyst. Should we be acid or base? Okay, and that's what this slide kind of asks about, is under what conditions should we be doing this mechanism? And really, acidic ends up being the best option. To go fully basic, to make that nitrogen basic, is really hard. Okay, so it's just not feasible to reasonably do that, and it introduces a whole nother mess of reagent problems. But if we go stupidly acidic, that neutralizes the nitrogen's activity as a nucleophile, and the reaction falls apart also. So we end up having to use a very mild acid catalyst, so small concentrations of acid. That slows the reaction down, and we end up being very heavily equilibrium dependent. Okay? And we have to do things like Le Chatelier, tons of amine, and remove water from the reaction to help push this process along. Okay? But the hope is that that goal of the imine product, okay, that pi bond between the nitrogen and the carbon, is that much cooler and useful that that's what we want. Okay? So we do have to be careful with the acid, okay, because of that nitrogen base conditions. That very first step is very likely to protonate the nitrogen, so you need mild acid conditions, and it can sometimes be written as mild acid or cat acid, or catalyst. There's the word. Okay? So be kind of aware of that adjustment in this. This is, again, very equilibrium dependent, just like our acetal. So I could reverse this process. I could start with the imine, add water, and take it back to the carbonyl, okay, which we kind of saw in the previous video. We're looking at the nitrile. So with that, as much as it kind of seems like I haven't talked about a whole lot, we've really covered everything that you need to be able to answer questions now with nitrogen as a nucleophile in these systems. Okay? Some of these questions are a little bit trickier than others, but again, I'm going to say go ahead and pause the video and attempt to come up with answers. And this might even be one that I shove into play pause it, so you may be forced into that, but we'll see. So pause, and now we can continue. And that very first reaction does have some, I'm really disliking the stupid looks on my faces. So let's try and look at the camera. There we go. That's a little bit better. If we look at that first reaction, note that there is a big difference here, or a slight difference. In the previous examples, we had a hydrogen, not a nitrogen, or not a carbon. Right? Does that change the overall result? Okay? If we kind of summarize what we saw before, when we had the NH3, we went through and did this. So the result was that I had to lose 2 hydrogens from the nitrogen so that I could make H2O. Well, if we look at that starting structure, do we still have those 2 hydrogens? Well, yeah. So get rid of them, make H2O. There's H2O, so I got rid of the oxygen, and now replace those 2 bonds to hydrogen, to our nitrogen, CH3. And there it is. What we've now formed is an imine, okay? Also potentially known as a Schiff base, depending on what your preference is. Okay? Next question down. Instead of it being a hydrogen or a carbon, we made it an oxygen. Okay? And the big challenge with oxygen is that we have lone pair electrons. Okay? So how should that reagent act? Should it act as the nitrogen nucleophile or the oxygen nucleophile? Hopefully you should recognize that nitrogen is a better nucleophile, and it's a better nucleophile because it can't stabilize the electrons as well because it is less electronegative than the oxygen, which means what we're looking at is the nitrogen acting as our nucleophile. We'll ditch the 2 hydrogens. And we get H2O again. And we've got our answer. Okay, so everything's fine and dandy. This seems to be kind of a decent pattern for how we work through this. Of course, things get worse. Remember, we had hydrogen. We've now replaced it with a carbon, but we took another hydrogen and we replaced it with a carbon. This means we can't clear 2 hydrogens out of this. So what we might do is attempt kind of the mechanism through this, attack, break, see what our result is, and this is going to look kind of messy here. Our new bond, here's our nitrogen, okay, with that hydrogen on it, it would be positive. Old bond out to our oxygen with its negative charge. Well, we could fix some of that by getting rid of 1 hydrogen, which would fix the positive charge. And we could put the hydrogen on there. Okay, so that would fix that. Remember, where we wanted to push, though, was doing that full kind of replacement. We do still have electrons on that nitrogen. Those electrons could come down and force this out, particularly if we were still kind of under those mild H+ conditions. We could form that. The result of that, however, double bond to our nitrogen, forming our kind of standard imine, would then have this positive charge on the nitrogen. And that's not particularly good. Okay? Also, where did our hydrogen come from for that oxygen? We said from the mild acid. It turns out that this structure makes this hydrogen very acidic. Okay? It's very acidic because that nitrogen doesn't want to be positive. So what can end up happening is our oxygen, with that potential negative charge, can come in, remove the hydrogen, shuttle electrons, go across, and what happens? we would have the pi bond between the carbons. We'd have our nitrogen up top with its lone pair. What we've now formed is what is known as an enamine. Okay? Ene for the alkene, amine for our nitrogen. We've put them in conjunction next to each other, which should sound kind of familiar. It should sound like the enol. And if we revert this parallel back to an oxygen instead of a nitrogen, yeah, this is exactly it. This is the enol form for a nitrogen compound. Okay? Why does it become a useful structure? Well, those electrons could come down, shuttle out, and we now have an active carbon nucleophile. So this becomes a very synthetically useful species, and it's one that shows up in a lot of different places. Okay? We will talk about the enamine and again a little bit later when the synthetic utility of the asymmetric enamine comes into play. Okay? But realize that the enamine that we're forming here is symmetric because we have the same substitution out either end of our starting ketone. What happens if it's asymmetric? You should take a swing at it and see what you think happens there. With the ketone, remember we got a balance between kinetic and thermodynamic. We're still going to get two potential products, a kinetic and a thermodynamic for the enamine, but interestingly, only one is prioritized. The other one doesn't form to any significant extent. That's a tricky conversation to have. We'll talk about that when we get to the actual application of the enamine later on. And then the last one, if we go through and look at this, I'm switching up the question now because I'm asking for what is the material that we would need in there. Okay, so what we would do is look to the product of that first step and note that the change is that we have those two nitrogens. Remember, if we're reversing this, we would need that H2 to make our water and an H2. That substance is known as hydrazine, and it's a perfectly valid reagent that allows us to form that structure. This is a particularly interesting question because the next part, okay, is kind of why we use hydrazine. That dinitrogen structure, that diazo aspect, isn't really all that interesting until you actually understand what's happening in that green spot. And what's happening in that green spot is this. You might be like, well, you just drew the ring. Exactly. Okay. That sequence of reagents, step 1 are hydrogen, step 2 sodium hydroxide and water, results in the complete removal of the carbonyl. Okay. We have no more pi bond there. Okay. And it's now fully reduced down to our alkane. And that could be useful if we wanted to get rid of everything. That is kind of a neat mechanism. It's a stupidly long one, but the next slide is actually going to address that. So let's go ahead and advance and look at that. This is what that reagent does. We do our NH2 structure first, right? And it doesn't have to happen as 2 steps actually, but I broke it into 2 steps to make it a little bit easier to see. That's going to go through with our NH2 reagent, okay? That's going to convert that structure into our imine compound, okay? Which I should actually be showing in black. So I'll go through and do that while you're now thinking about what would the rest of those reagents go through and do for us. Said black, come on. Well, hopefully one of the things you note is that those reagents are reactive, and in particular most reactive as the KOH, which is our OH minus. That is a strong base. that strong base could remove a hydrogen, left off the carbons because they're going to get in the way, could remove a hydrogen. And you might say, well, why would it do that? That then puts the electrons onto that nitrogen, and that's not particularly stable. Okay, and you might be correct in that statement, but what we have to do is propagate this a little bit further to see what this could potentially do. There's that negative charge now on that nitrogen, our H, and we have that remaining lone pair. Okay, that negative charge could donate in to our other nitrogen, because the other nitrogen's electronegative. Why not pull electrons in? That would then exceed the octet on that nitrogen, so it would have to take that pi bond and eject those electrons to something else. Okay, well, what else is floating around in solution that could accept electrons? Well, water. Okay, this is a tricky one to go through and draw out. So I'm going to draw some of it and then ask you to figure out the last remaining bonds, or spend some time to figure out the last remaining bonds. Okay, so there's our general skeleton. Where should that hydrogen go? It is very common for students to place that hydrogen on the nitrogen. Okay. Did that fix its octet issue? 2, 4, 6, 8, 10. Well, dang, placing the hydrogen on the nitrogen actually doesn't fix the issue. If we go back and very carefully consider what our arrow is doing, that arrow is showing the electrons moving away from the nitrogen, which means they're moving towards the carbon. That new hydrogen is connected to the carbon. Okay? For those of you thinking about the chemistry there, that means that carbon is carrying a negative charge. It is. Okay? This reaction is forcing the carbon to act as a base. Okay? And we might say, well, why the hell would it do that? Okay? And you're right. It's probably not likely to do that. Okay? So our equilibrium probably isn't really favoring any of this to happen. Remember how I said equilibrium is a problem? Okay? Well, we're still in a basic environment. This whole cycle could start again. Okay? And this time I'm showing it happen through a reduced amount of steps. Okay? So mechanistically it's a lot more complicated, or not a lot, but broken into a lot more steps. And we'll see that when you look at the textbook, and I honestly don't remember if I've got the full mechanism written out here. Okay? But let's look at what this multiple sequence of steps would do. Okay, so it's all of the arrows kind of in one thing. Well, the ring didn't change, so that's still there. That backbone didn't change. We still have that hydrogen. Okay, if we take a look, this bond went out to share with a hydrogen. Again, bad geometry there. But then that nitrogen is no longer connected to the structure, right? If we now look, the double bond there was still there, and we have more electrons there, so we would now have a triple bond. We would now have that nitrogen with no hydrogen connected to it, then we'd have H2O out here. We would have reformed our OH minus over here. And you might say, well, dang, that was a lot of stuff. Why would it bother to go through and do that? Well, the answer is actually right there. Okay? Written another way, that's N2. N2 is an exceptionally stable gas. Okay? So it is not, once it is formed, it is not likely to reverse the reaction because of that triple bond and the exceptional stability within it. Not only is it not able to reverse it based off of reactivity, it's a gas, it bubbles out of the reaction. I can't reverse that last sequence because the reagent to reverse it is literally not there. Okay? So even though all those other steps may not really be driving towards a product, they're forming in small amounts. As soon as I form that nitrogen gas, that step of the reaction is solely favoring the product. Based off of equilibrium, I'm constantly removing products. The reaction eventually cycles all the way across where I have now fully reduced the carbonyl away. Okay? And that is a pretty fascinating reaction that I drew here in very few steps, largely because I skipped the hell out of what's going on in there. Okay? Each of those steps of those arrows is pretty much its own mechanistic step. Okay? So there's a lot of mechanistic steps behind this. But what this does is it takes advantage of the reactivity of the nitrogen to replace the oxygen, and then because I have that extra nitrogen in there, I can also go through and form nitrogen gas, bubble that out of the structure, and I can now entirely remove the carbonyl. That's pretty neat. Okay. And let's see. I don't think I've got the mechanism drawn up. Yeah, I don't have the mechanism there. I know our textbook has it, and I would highly encourage you to take a look at that if you want a little bit more information. We move into chapter 19. We're going to see a couple more reagents added to this list of being able to reduce carbonyls, so trying to pick up on it now might not be a bad idea. Okay, with that, thanks for listening. That was kind of a fun one, kind of interesting stuff. And I should stop the recording